to do now is I have a demonstration where I'm going to basically be pulling up this the smart timer code that we had earlier, right, the device driver, just briefly look at that and show how we would modify the Zynq Z.dts file, right, so that it now knows that there is a particular peripheral present over here. But as you will see, right, when I go through the demo, I'm sort of taking one shortcut over here, because in addition to this timer that we have been using all this while, I also wanted to bring in one more type of peripheral, right, and this is a slightly more complex peripheral in some ways. What I mean by that is, the one that I'm going to consider as an example over here is, let's say that at some point in time we want to write a hardware module for something like a Fourier transform, right. So okay, and we'll get back to this later. The reason why I mentioned it now is that when we look at the device tree specification that we have for the new module that I'm going for the new kernel that I'm going to boot up, you will see that I have actually added two things inside the AXI bus, right. So under the AXI bus, I have added these two modules. One of them is called the smart timer. I've given it a label, the smart timer 0. As you can see from the rest of it, that label is sort of optional, but it's probably useful to have, right. What does it say? It basically says that this smart timer module is compatible with the string Acme smart timer v1. It is going to be present at this memory location 0x70000, etc. and it has a window size. The number of addresses that need to be allocated for this is 0x1000. So in decimal, that would be about 4096 memory locations that are given for this, right. Similarly, I am also defining another block called the FFT32, right. Now this is compatible with a different string, and as we will see, we have a different driver which claims to be compatible with this string, which loads at another address. Okay. Now of course, all of this only matters if my hardware actually is connected on the AXI bus at this particular address, right. Keep that in mind. The device tree specification by itself is only as good as how accurate it is, right. In other words, the actual source of truth is how I have built my hardware. So when I create the SoC, I need to know on the AXI interconnect at which address location is it that I have actually connected this smart timer, where have I connected the FFT. Then based on that, I write my device tree specification, right. And the DTS must provide exactly the same data as what I used in my hardware, otherwise it's giving wrong information to the kernel. But once this DTS has been written in a certain way, I can then go ahead, and there is a standard way by which I can compile this, right, where effectively what I do is I use this function, this program called DTC, the device tree compiler, right, which basically takes as input a DTS specification, creates as output a DTB, a device tree blob, and in our case, it's going to basically take this modified DTS that I have got and create a DTB corresponding to that, right. Now when you actually run this, you might find that it sort of gives several warnings over here. In most cases it's possible, as long as they are warnings, you can sort of ignore those, right. If you do see such a thing, then just ignore it for the time being. We can sort of get that sorted out later. But the interesting thing is, at this point in time, my device tree has been modified so that it actually knows that there are two extra pieces of hardware corresponding to this location. Now that's for the device tree. How do I actually modify my hardware? Now so far we don't have any modifications in the hardware. What we are doing instead is, I'm using the Renode scripts, right, in order to actually specify what my hardware looks like. And just to recap, right, the way that I'm going about creating the Renode script is, I load the platform description corresponding to this ZedBoard, but here I can basically sort of add in an overlay, right. An overlay is some additional information corresponding to some other things that are attached on my system bus, right. So let's take a quick look at what's there in that overlay, right. all that it says is, it says there's a smart timer, right, which is basically a mapped memory, right, at sysbus this address 7000, right. And similarly, I also say that there's one more device called an FFT, right. I'm calling it FFT0, it doesn't really matter. The important thing is it says that it's at this address 7000, 1000, okay. And by doing that, effectively, now as far as the Renode emulator is concerned, it's going to say that if you try writing into those locations, it will just take it, make a copy of it somewhere, because it will treat it as though you are creating a memory block at that point. If you try reading from it, it will give you back data corresponding to whatever you wrote there last, right. So Renode, in other words, at this point in time is going to take care of emulating our hardware for us. It just creates a fake piece of hardware so that we can at least write and see whether the system is able to pick that up. Okay. Now, with all of this in mind, we sort of have our Renode setup in place. Now let's look at what our platform driver code looks like. Right. This is the platform driver corresponding to the smart timer, right. And what we have over here is, you have certain things, right. For example, there are some basic structs and so on that we define over here. You will notice that there are a few functions. For example, there is this thing called control_show, right. This is useful for us when I want to, for example, read the value of the control register from the sysfs, right. And similarly, there is a control store which basically says what happens if I try writing into that particular location in sysfs, right. So these kind of functions, control show, control store and so on, are used by the sysfs create group in order to say, okay, I have a variable called control and I should create a file corresponding to that. If somebody asks me what is present in that file, call this function, right, basically read something from this offset control, right, take out only the bottom few bits, that doesn't really matter, and then just convert it into a string. So use this function scnprintf in order to take whatever was the value that you just read out and convert it into a hexadecimal string so that it can be displayed, right. Control store does something different. It basically says, first try to use this function kstr control store uses this function kstr to ul, right, in order to actually take a string and extract an unsigned long number, that is to say a 32-bit unsigned number out of it, right. So that's the str to ul function. The kstr to ul means that it is something that can actually be called as part of a kernel driver, right. Remember what I told you about not having access to libc. Therefore, the kernel has to sort of re-implement many of these functions in a way that can actually be used internally, right. So what we have over here is, it basically says I'll extract that value from whatever it is that you type in on the command line, convert it into a number and then call the writeL function in order to actually take that value and write it into stbase plus offset control, right. In other words, write into that memory location. Similarly, we can see that there is something for the period show and period store, right, duty show, duty store. And you will notice that after each and every one of these, there is this macro that we call, where we basically say this is a device attribute. By just calling this device attribute over here, we are sort of telling that sysfs create group that I need to create an attribute file for this particular pair of functions, right. So by saying duty over here, it automatically looks for a function called duty_show and duty_store, because it has been defined as a read-write attribute, right. And by doing that, I can basically see what is the current value present in control and also write new values into it, okay. And similarly for status as well, right. And finally, I basically say, okay, these are all the different attributes that are being used for this particular system. I create an array of those, right. The array has to be properly terminated with a null string, and I need to make sure of that, because these are things where within the kernel, if you don't properly terminate your arrays and so on, that can cause all kinds of problems. So we also have the smart timer probe function, right? We briefly looked at this in the slides. We have the allocation of memory for it. We get the resource information from the platform, in other words from the device tree, do the devm based IO remap, which essentially registers it and keeps it ready such that as and when the driver needs to be removed, the memory can be freed up, right? Sets any driver data that is required for this platform, and finally creates the system group, right, the file system. And finally it prints out a message saying the smart timer was bound at this particular address corresponding to whatever was the value that it got. Okay. Similarly, when I want to remove it, I basically say, okay, I remove the group and I'm done, right? And what we can see finally is, as we saw, right, I need to have this OF match array which says that it is compatible with this Acme Smart Timer V1 because that's the string that I gave in my DTS. And finally, I have this platform driver struct which says that whenever I probe or try to load the driver, call this function smart timer probe, which is this function over here, right, smart timer probe, right. So what I have here, in other words, is effectively this is storing a pointer to that function. Similarly, this remove is a pointer to this function, smart timer remove, right. So having done all of that, I can finally call this function module platform driver. I give it this smart timer driver struct as an argument. It goes through all of these and basically does the appropriate job of loading the device driver. Okay. So let's see what exactly happens when we do something like this. Before that, when I show you the Renode, I also want to show you one additional modification that I have made in the init script, which allows us to sort of automatically load the driver when the system boots up, right. And it's actually, this is a very simple kind of modification which basically says look through all the things that were described in the device tree and try to load modules for them, right. There are other ways such as using the user space events and so on, by which module drivers can be loaded at runtime as required, but for now I'm going to sort of use a sort of brute force approach where I just say look at everything that was specified in the device tree, try to load a module for it, right. And the way that that is done is through running a script. You might recall that when we were sort of setting up the initram fs, what is the initram fs? Just to recap, my kernel that I am compiling over here does not have access to a full-blown file system. I do not have an SD card, I do not have a disk. All I have is something where I create something which looks like a file system, but it is all stored in memory, in RAM, right? And this is usually called an init RAM disk or an init RAM file system. So that initial RAM file system I need to populate, and what I have done is as part of that I create one very specific script called init, which as a matter of convention is the very first program that Linux systems run when they boot up. Okay. So the Linux kernel has sort of hard coded into it that name init, which says when the kernel has finished loading up, it should try to access whatever file system it has access to, see if there is a program there called /init and try to run it. And that's precisely what this does. Okay. And as part of that, as we'll see, it does a few things, mounting certain of these virtual file systems, printing out a message, user space is up, and then over here we set it up so that it basically goes through all the platform devices that it has been able to identify. All of these entries would have come because the kernel went through my device tree specification and created entries in this virtual file system folder. It tries to run the modprobe command on them and to load them in, right. So as we will see, when we actually run Renode, the system will actually boot up with all of this information in place. So let's go ahead and do that. So I start up the Renode terminal, right? And once it has come up, I need to insert or import the Renode script, right? And in this case, it's called week6_zinc.renode script. The script itself I showed you, it essentially creates a machine platform, loads the overlays, and then it goes through and it sort of loads up the entire kernel and so on that has been done. Now there are a couple of steps that I have skipped ahead over here. I already compiled the kernel that I showed you corresponding to this smart timer, loaded it into my initram fs, and then recompiled my VM Linux such that it has that content corresponding to that initram fs loaded into its correct place, right? So a couple of steps that have already been done because they were exactly the same steps as what was done in the previous weeks, right? And is documented in the code that is there. So you will need to follow all of those if you actually want this to run. It has to be with the updated version of the kernel because otherwise it won't contain the drivers corresponding to the new devices that we have got, right? So when I load this, what you can see is that it sort of pops up these two windows, right? Because I have asked it to monitor both UART0 and UART1, right? But there are a couple of things that we can, for example, look at over here, right? I can ask sysbus what is at this particular location, and it tells me that there is this smart timer registered at this address. How was it done? This has nothing to do with the Linux kernel or the DTS. This was done as part of the REPL script, right? The one which basically the overlay script that I showed, which basically says I have a smart timer at this particular memory location. It also means that if I ask it for this other address, right, 1000, it says that the module FFT0 is registered over there. And just to sort of confirm both of those, we can go look at our actual code out here. Inside the overlays, we can look at the peripherals, and as you can see, right, it basically tells me that there is the smart timer at this address with this size, and there is the FFT0 at this address with this size, right? So Renode, in other words, is just sort of going exactly based on whatever it has in terms of whatever was specified to it as part of the Renode script or the REPL, right, the platform description. Okay, so far so good. Now let me start and boot up Linux, right? So when I give start, it just says starting emulation and then doesn't really print anything else beyond that. That's because there's a lot of work happening behind the scenes. But I can, for example, look at something like what is the value of the program counter, and I'll find that it's constantly changing. This is because the system is actually going through a booting process. It is actually running code, right? What do these addresses correspond to? I don't know, right? I mean, they correspond to various different parts of what's present inside the kernel. What is important to us is that a bunch of messages have been getting printed out on the screen, right, on UART1, also on UART0, right? But UART1 is the main thing that's of interest to us because that's the one that's actually got mapped internally inside the kernel as the actual console for this system. So we just wait a moment for the system to finish the boot up process and finally drop us into a shell where we can start typing commands. So this can take a significant amount of time depending on the processor on which your emulator is running, because remember, after all, that what is happening is Renode is an ARM system emulator which is in turn running on your laptop, desktop, or the virtual machine that you are using for running these experiments, which is most likely an x86 based system, right? So we are trying to emulate an ARM based platform on an x86 based system, which means that it is naturally going to be a little slower than just running code directly on the processor, right? But as you can see, it's not terribly slow. You can actually interact with it in real time, right? Now, the interesting thing is you might have noticed that a few messages come right at the end. For example, there is this user space up dropping to shell, which we know was there in our init script. After that come a couple of fairly interesting messages, right? It basically says there's a smart timer platform loading out of tree module, and it tells us that this particular smart timer has been loaded at this memory location. Remember, all of this was picked up from the device tree specification, because what we wrote was a platform driver, right? Now we also have, of course, the FFT block demo, but I have not really discussed what the FFT block demo does yet. I had loaded it. We'll look at that in a moment, but for now let's just look at what happened as a result of loading in this smart timer, right? What we can expect to see is that under the /sys file system, which is after all a virtual file system corresponding to the various devices and so on that are present inside the platform, I can look in this particular folder called sysbus platform, right? And I'll find that there is, for example, something called devices and something called drivers, right? And I want to sort of go deeper and look inside, let's say, devices, right? And it turns out that there are a whole bunch of different things. Well, one of the useful things that we can see over here is this thing called the smart timer, right? So I can go inside and look further into this, and sure enough, I start seeing these different names, right? There is control, there is duty, there is period, and there is status. And we know that these are names which we registered as part of our sys attributes, right? So we have already seen this demo, but just to sort of, confirm it, I'm going to go through and do this once again. I can, for example, echo or write a number, right? Let's say 234 into sysbus platform devices smart timer / period, right? And if I then ask for the data present over there, in other words, I run the cat command from here, right? It shows me this number EA, which is basically the number 234 converted into hex. I can also go here, right, and try reading back the value, read the word which is present at this location, 7004, right, which basically corresponds to the memory offset corresponding to the period variable. And it turns out that yes, I have this value EA written over here, right. So what that is telling me is, remember that whatever is displayed over here is being shown to you by the emulator. It does not know about Linux, it does not know that there is an operating system running internally, it just is executing instructions corresponding to our platform. On this side, through Linux, I managed to expose a file system based interface which allowed me to directly change the value written in a particular memory location. Of course, this is something that we have seen earlier. The main difference that you might have noticed at this point is, when the system booted up, it automatically ran that mod probe. It just basically searched through all the things that were being specified in the device tree and went ahead and loaded the devices, right? So this is more or less how actual systems work, right? They try to sort of say, okay, everything that's present in the device tree, let me go and see whether I can load in the corresponding driver for that, right? And by doing so, you can find that, at this point in time, when I do ls mod, it turns out that yes, there is a smart timer module that's been loaded over here, right? There is also an FFT block demo module, which we will talk about in a moment. So both of these, just because of the fact that I had registered them as modules and had then gone ahead and done a mod probe at boot up time, have got loaded into memory and are then visible as different devices that are present in my platform bus.